So, kicking off this afternoon, we have Stefano Lorenzi from Polyme, Guido Mazzotti from Polyme, and Torsten Hollands from GRS, who are going to be presenting to us the open source Modelica-based library and coupling with existing simulation tools assessing nuclear safety and techno-economic viability. Stefano, the floor is yours.
Thank you, Jessica. And as you mentioned, this presentation will be more on the technical side. The presentation wants to collect all the outcomes that we have produced in the work package of Tandem dedicated to the development of modeling tools and also methodology for the assessment of, in general, hybrid energy system. So we have started from this, let's say, analysis framework because once again, one of the objectives of Tandem was also to develop methodology for studying nuclear hybrid energy systems. And as you can see, if we want to tackle the problem, it's quite complex. We have to link some context analysis to understand which are the scenarios that we want to simulate, to study. We have mentioned before that, especially for cogeneration, we really need to have in mind which are the requirements, which are the needs of the final uses. Then we have also the part related to the modeling, but then modeling itself, it's not enough. We have to frame our analysis in a techno-economic framework. So we have both on one side, the layout optimization, dispatch optimization. We have also the system analysis that we have for sure to take into account. And finally, the policy recommendation that were already presented by Jessica. The presentation today this presentation will mainly focus on the modeling and methodologies that we have developed during the Tandem project. So at the end of a project, there is it's a little bit sad because it's finished 3 years of intense work, but I think that there is one very important question that we have to answer. And the question is, why is the world a better place after the Tandem project and specifically after the work package 2 activities? At the end of the day, we have found 3 answers to this question, and I will tackle the first one, and then there will be Guido and Torsten to tackle the second and the third one. But at the end of the day, we were able to develop an open source Modelica library. So we have already mentioned this in the Claire's presentation. So we have developed a modeling tooling that it's open source. So everybody can use and everybody can exploit the work that we have done. This library was aimed to simulating the more technical aspect of the behavior of power plants of the different system coupled to the within, let's say, the nuclear hybrid energy system, obviously including the nuclear part. So the SMR Tandem was mainly focusing on light water SMR, but not only, and also to the other components that represent our integration, meaning that hydrogen plant, desalination, thermal storage. The second big, let's say, outcome that we have achieved is not only we have developed the, let's say, the bricks that the building block for developing a possible simulator for the hybrid energy system, but we have developed 2 hybrid system simulator. One for the first case, the district heating case, and the second one for the energy hub cases that have been developed for the techno-economic analysis and the safety analysis. And in the next presentation, you will see the the application of these 2 simulators. Third one, we have also focused on the safety part. So we were asking ourselves which is the best way to exploit the work that we have already done for the Modelica library. And in the third, let's say, this outcome, we come up with a way to couple, to exploit both the safety codes that are well suited for representing the NSSS, so the nuclear island of the reactor, and the Modelica models for the integrated energy system in order to study in a specific way, which is the effect of this integration between the different energy sources, energy carriers, and energy storage systems. So focusing to the first part, the open source library, as I mentioned before, the Modelica library was needed in order to achieve both the techno-economic study, so to be able to include very specific technical details to the techno-economic studies, and on the other end, to be coupled to inform safety codes that the balance of plant is, let's say, more complicated than the usual one in which you have just electricity production. The first step that we have tackled for the TANDEM library was starting from the functional requirements that are asked for this kind of library. So we ask ourselves which are the key feature that this library was has to have, the must-have for our modeling tool. And here you can see that we would like to have something that it's able to have a dynamic response of our systems. One of the most challenges of an hybrid energy system is to, let's say, coordinate the different input and output in terms of energy flows, so both electricity and the thermal flows, in order to be able to exploit the best from our system. Obviously, for a more technical part, we need to keep trace of the process variable during this variation. So at the end of the day, we come up with the Modelica library. Another important, let's say, feature that we would like to keep is a lot of partners in the TANDEM consortium had experience in Modelica. So we should not reinvent the wheel, but we decided to reuse some legacy library that have been already developed by the partner and share the library in a more general framework, the Modelica TANDEM library. And on the other end, try to develop connectors that make possible to use both the best from one library and the best of the other library. Here you can see the models that have been developed for the library. You can see the more nuclear part with the NSSS and the balance of plant, electrical grid, district heating, storage, renewable desalination, and hydrogen production. Always in the first phase, we have decided to which are the components for which we need a very detailed configuration. And here you can understand that the simplified keyword here is to mean that since there are some components that require just an electrical connection, we decide to simplify the modeling. And these are the supporting library, so the legacy library, and you can see that they are coming from also from different partners. The other important, let's say, message that we want to share with you is our general approach that we employed for the library. As I mentioned before, I mean, this is a general rule in modeling. Try not to complicate much more than it's needed the model of the components. So that's why for the only electrical coupled components, we decide to keep a simplified modeling strategies. as I mentioned before, different Modelica libraries have been used for the modeling. And so we have developed ad hoc adapters in order to be able to, for example, take the model of the N-SSS from one library and then couple with the balance of plant from another library. And then we have considered mainly two coupling approaches. One thermal coupling, and the second one of the fluid coupling, in which we can decide the degree, let's say, simplified or a more refined coupling between the two subsystems. Obviously, these apply for the strategy in which we decide to couple component coming from two different libraries. Here you can see in a very brief way some of the an example of the module. In this case, we take the data from the ESMR, European SMR from the Elsmore project, and we develop two models for the N-SSS and 3 models for the balance of plant. This was mainly, let's say, driven by the fact that in some cases you need different degrees in your model of the balance of plant. So one model, it's the so-called simplified one. The other one consider, for example, it's more let's say dedicated to transient in specific situation. So if you look at the library it's once again open source, freely available in the GitLab repository. You can find the link in the TANDEM website. As mentioned before, how can we use this library? You can develop your customable simulator. You can assemble your own simulator with the available bricks. You can also develop your own bricks depending on the needs. And the two main, let's say, application is to use to study the operational transient, like heat load transient. We want to study how the system responds to the daily or even the seasonal variation of the heat, the response of the electrical needs, and so on and so forth. And this is the, let's say, application more related to the techno-economic analysis. The second one is the application for severe accident. So try to really to understand which is the difference, which is the, if any, the additional concern that we are introducing when the balance of plant is used also for cogeneration application or in general polygeneration application. So this is the very big first achievement that we have developed, so the open source Modelica library. Now I give the floor to Guido for the second big outcomes, which is the development of the two hybrid system simulators.
Yes, thank you. So with this slide, I just wanted to show a practical application of the library, which is the modeling of the two case studies that were introduced by Claire this morning, which are the district heating case, for which we considered the district heating network in the Helsinki metropolitan area as a reference, which as today is driven mainly by fossil fuels, and as part of the decarbonization strategies investigated by TANDEM, we considered the potential integration of a light water-cooled SMR to this grid. And the second architecture is the one of the energy hub case, where we are talking mostly about an industrial district, where we have several electrical and thermal power sources that are strongly interconnected with each other and with different industrial processes, and like hydrogen production, desalination, and so on, to provide commodities to different end user segments. Before diving into the modeling activities, we carried out an intermediate step, let's say, a preliminary investigation, to translate this, let's say, more conceptual architecture in a more detailed plant layout, which you can see on the right-hand side of the slide. And in particular, we try to build and provide a representation of this district heating network in a more detailed manner, considering also heat exchanger, transmission lines, valving systems, pumps, and so on, to be able to translate it into the Modelica language and account for the dynamics and the phenomena that are occurring in the single components of this district heating network. So if we look at the simulator, this is the simulator resulting in the Modelica language. And I think that also from this picture, you can really appreciate the advantages of using an object-oriented modeling language like Modelica, since it was possible to really take the bricks, the single bricks in the library, and to assemble them with each other in a quite flexible way to build this more complex and let's say comprehensive energy system architecture. In particular, you can see the bricks for the nuclear steam supply system, meaning the primary side of the nuclear reactor, the steam cycle, and also the district heating network, which is based on the architecture that I've been showing before. Here I reported just an illustrative transient simulation to showcase how a simulator like this one can be used. Essentially, we provided several set points in terms of heat demands and temperature requirements for the Helsinki network. And with the simulator, we were able to investigate how the power flows are allocated within the system. For instance, from the nuclear power plants to the network, or from other heat sources, or the exchanges with other district heating networks. And of course, with the simulator, we are able to account also for the dynamics, and also inertial effects or fluid travel time and so on. Moreover, we can investigate different control strategies. In this specific example, we considered temperature control strategies, meaning that, as you can see from the second row, we are able to control the temperature levels in the district heating network according to predefined requirements, which depend on outdoor conditions. And last but not least, we are also able to track more system-specific variables, let's say, like the power produced by the nuclear reactor and how it is affected by a variable heat extraction for cogeneration purposes. And also looking at the secondary side, the electrical power produced by the steam cycle, which of course can be useful also when it comes to economic consideration of the system, since of course, according to this profile, we will have some associated revenues from the electricity market, for instance. If we look at the second architecture, we did a similar approach to translate the conceptual scheme into a more detailed architecture. And in this case, we focused only on some specific components, considering just the SMR as a power source operated in cogeneration mode, and as an industrial process, the hydrogen production via high temperature steam electrolysis. As you can see, we have also other power sources, which whose operation is coordinated together with the SMR to meet both an industrial load and the energy requirements of the hydrogen production plant. And for this specific case study, we decided to investigate two different architectures. A coupled architecture in which the steam cycle is directly connected to the hydrogen production plant via an intermediate oil loop, meaning that any variation in the operational state of the hydrogen production plant will directly affect the steam cycle operation, while on the other hand, in the decoupled architecture, we have a thermal energy storage system, which is essentially separating the operation of the steam cycle from the one of the hydrogen production plant. Now, if we look at the simulator, we were able to build it adopting a similar approach as mentioned before, meaning that we can combine the bricks available in the TANDEM library through a plug-and-play approach to build a simulator. We have essentially the same nuclear power plant model that I've been showing before, but this time we coupled it to the thermal energy storage system. In this case, it is just the coupled architecture as an example, and to the hydrogen production plant. And here you can also see the feature that also Stefano was describing, which is related to the use of different libraries within the same dynamic simulator. Since, for instance, we coupled the thermal energy storage system, which is based on the thermal power library, with the high temperature steam electrolysis module, which is based on different libraries since it was built by different partners of TANDEM, and we were able to couple them through dedicated adapters. To conclude, I provided also here an illustrative transient scenario. Also in this case, you can see how the power flows within the system are both the electrical and the thermal power flows are allocated to meet the specific industrial user requirements, considering also curtailment in this case, since we are assuming that we don't have a connection with the power grid. And then you can see also how we are able to track other variables that are highly relevant for the operational, for the dispatch strategy of the system. For instance, we have the levels in the storage devices, which, of course, when it comes to the maximal storage capacity, it represents a constraint for the operational strategy of the integrated system. And then once again, we have other variables that represent valuable commodities that have an associated revenues to be accounted for the integrated system. I think this is it from my side. I'll leave the floor to Torsten for the economics part, for the safety part, sorry.
Thank you, Guido. So coming to the third question that we have developed, or point that we have developed a coupling scheme for between the safety codes, that means Qatar and Athlete on the one hand, and the Modelica BOP models on the other hand. So that means we don't consider the whole system, but just, let's say, the BOP for the interface, but I come to that later. What we have here, this is a hybrid energy system, and we have on the left side the SMR and the power, the BOP for the power conversion. And this is that's what was just described before. And the main, the interface module is the BOP. That means the simulation of the turbine generator unit and all the IOC systems. What is needed coming from the hybrid energy system, and as a boundary condition for the SMR. So that means we built an interface between the BOP and the reactor, which was in that system a Modelica based system, and coming to safety system. That means the SMR itself will be simulated by safety codes, which are mechanistic codes and more detailed than the Modelica model. And therefore we find some scenarios like a normal operation, AOOs, that means abnormal operation, and design-based accidents, but Walter and Paolo will talk about that in the next presentation. That is not an easy topic to find any scenarios suitable for cogeneration. But what do we really want to simulate? It is assumed that a multi-SMR units are to be built at one location. That means we have more 5 to 6 small modular reactors, not one big one, but for the simulation or the coupling and safety analysis, we choose only one single unit because it's the first approach, and to make sure that there are no interconnections between the reactor, just one is taken here. And how it looks like can be seen on the right side. It's the ESMR data set description, which was built up in Elsmore, and it has total thermal power of 550 megawatt and electric power of 167 maximum. But that can, of course, be split for cogeneration purposes. Compared to that, and yeah, EPR, how it was built in Flamerville or in Finland, has 5,300 megawatts thermal and 1,600 megawatt electric. That means more or less here 8 small units are needed to generate the same number of electricity compared to one big one. But I think we know all the advantages or disadvantages between small modular reactors and large light water reactors. Yeah, and what are safety codes? What I just said before is that they are used to assess the safety of reactors. In that case, light water reactors. They are used for certain time, or since it was able to use computer codes for the evaluation of reactor, and they're used by utilities, vendors, TSOs, regulators, or TSOs and Harvard regulators and so on, to judge what happens in a reactor case, or in incidents and transients, or accidents like DVAs. And what we use in the frame of TANDEM was, on the one hand, on AC2 Athlete, which is developed by GRS, and part of the code package on AC2. That means it's the thermal hydraulic part of it, dealing with, let's say, all scenarios up to DBA. And the comparable code is Qatar, which is used by CA and some other French companies. So it's a French package dealing with thermal hydraulics. So they both are more or less state-of-the-art safety codes. And that means that they are validated and have a certain number of developments that they are let's say trustable to be used for safety analysis. Here, just an example that it's much more detailed than maybe what was seen before for the Modelica model. This is just a sketch how it is for Athlete. That means you have a pointer or the other micro. Okay, so you have the reactor, then the containment. Okay, do it that way. Okay. So just to shorten this is a sketch how it's modeled, and you see that it's a quite complicated zone issue, and that system will be coupled to the BOP of the hybrid energy systems. That means you have a quite detailed model with a connection surface to the hybrid energy system. And exactly at that point, we have the coupling interface. That means, oh, it works. Okay, now it doesn't matter. You have the coupling interface. It's a feed water and the feed water line and the main steam line. This is just the interface I showed before between the BOP and the reactor. And how can it be done technically? Just as an example for the Athlete technique, but it's comparable to what was done by CA for Qatar and Modelica. In general, there's a Python surface around it, which does the control of everything, and there's a lot of so-called FMUs, which deals with, for example, with the control of the primitives, the BOP model, and all models which are needed and coming from the hybrid energy system. And on the other side, you have, let's say, the safety code as a unit that interacts with the hybrid energy system. Here's some details, but I think it's not important for that round. Just to come back to the next point, I think it was the question in the morning: what is about INC? Well, what is exchanged? So I took an example from Paolo, and you can see here that it's now I can do it. Okay, here you have the reactor, you have the feed water and the steamline, where you have the interface, and what comes from the NSSS is what it's to be controlled is the primary average temperature, the pressure for sure, and the pressurizer level. And how can that be done? By of course by moving the control rods, spray and heaters, the volume control them. So this is classical light water reactor techniques. There's nothing special for the SMR. And what is controlled by in the BOP or needs to be controlled is a turbine frequency, the turbine pressure, high, intermediate, and low level, and the feed water tank pressure, and that can be done by the turbine admission valve, feed water valve, intermediate pressure valve, low pressure valve, and tank valve. That means you have to adjust your valves, and this is also some actors or some points which needs to be adjusted to get stable conditions between for that coupled simulation. Oops, wrong direction. Yes, some examples when you to show that for the Qatar your Modelica level that the system runs plausible, and that can be used for the following safety analysis, and Paolo will show some results about that later. So I don't talk too much about that. And the same case for Athlete Modelica, just to show that for combined usage, that means 90% electricity and 10% heat, which is our cogeneration case, that the system is running and show plausible results that makes us able to trust what we modeled, and we can use it for safety analysis. Finally, to conclude, what was let's say the product of work package 2, that what Stefano and Guido also presented before, is that we have a library with a Modelica library with components also for the SMR, for the heat storage, for renewables as well, hydrolyzers and so on. And based on that, a customer simulator was built and can be used for the district heating and energy hub cases. Then TANDEM, due to the TANDEM activities, we are able, or we enable, techno-economic studies on the nuclear hybrid energy system, also with possibility for optimization, for sure. And what I just showed before, also to do some safety studies with a coupled system, and not only safety code application. And yeah, finally, the first version of the library was developed for the needs in the TANDEM project, but it also can support some further development of the on energy system integration when we have a nuclear and non-nuclear application. So that maybe even right now, but also in a follow-up project that can be further used to enlarge the range of applicability for that system. With that, I conclude our presentation, and we're open for questions for sure.
To the three of you. So we have around about 10 minutes until left for this presentation. So please feel free to ask any questions you may have. I see already a hand raised over here.
Hello, thank you very much. Is it working? Right, okay. Thank you very much. So, well, I know quite well the enormous work which has been done in this framework. So again, congratulations for what has been done here. But I will have some kind, I may say, a nasty question. The one is, okay, now we reach a point where you just mentioned that we have found some library which can be used, but the TANDEM project is over. Now, how to take benefit of the work which has been done in order to somehow disseminate and so valorize the effort which has been made, because of course it's an open source library, it's available. The question is, what about maintenance? What about communication? What about all the things which will maintain the library some kind of operational state and viable?
The short answer is you have to wait tomorrow when I will explain that. But I can share also some, let's say, thoughts that for sure this is a very important point, how to, let's say, exploit the TANDEM library. I think that we have three main challenges that can be synthesized with we should use or promote the use of the library. We need to maintain the library, and we would like to develop the library. So for the user, for sure, I mean, I'm encouraging all of you to use the library. We have also included, or we are in the process of including the library in the Encore initiative, which is an IAEA initiative. I'm looking at Molly Kate. Okay. That it's promoting the use of open source tool in the nuclear community. So this will improve the visibility of the work that we have done. Another action that we have already done is if you go to the TANDEM website, you will find the deliverable of the work package 2, in which there are the description of the components, which want to be a kind of user guide for the library. This is still, it's intended to be in the, let's say, try to promote the use of the library. Obviously, there are some challenges, and probably what we have to think about as consortium is try to create a kind of core community of user and developers. This will be of very helpful because we can also try to use the library in other projects. This is it's already occurring because Claire, you miss one project in your list, which is the endurance project. So it's an European MSR project in which we'll try to benefit from the library, including also another type of AMR, the molten salt reactor one. But at the end of the day, the most, let's say, this is obviously something that we have to decide at, let's say, consortium level to promote this core, let's say, group of user and developer in order to keep alive the library.
One simple question and one related to that as well. So are you using Dymola or Open Modelica for the Modelica execution?
We are using Dymola. Yeah. Okay. In principle, it's the components are compatible with Open Modelica. Mm-hmm. That's the let's political answer. In a practical way, Dymola is way better. This could be obviously a barrier because Dymola is a commercial tool, but in principle, we are offering the library as open source tool.
We've found the same thing, so I was curious. And with regard to model validation, how much has been done thus far? Do you have a plan going forward? Or I know we've discussed things like code-to-code benchmarking, things like that. Do you have a plan for that at this point?
Not for the Tandem project because it's ended, but this is something once again in line with the creation of a community that keep alive the efforts on that. And for sure, another point which I will add to my slides of tomorrow, it's also the validation part, because that's very important. We have done something on a very specific component like the N3S with the collaboration with EDF and Giorgio, which is okay there, but not for all the components. We are doing something for the hydrogen production in collaboration with some colleague of the chemical department, but it needs to be let's say to be continued because it's not enough.
I think we have time for one last question. Okay.
So can these models be extended to deal with, say, to achieve a sort of reliability analysis of sorts? I mean, can you inject faults, for example, or model faults and see how they would impact on the safety requirements, for example?
Yes, this has been done not here, but in a similar framework, in a nuclear framework in which we use a similar, let's say, modeling approach in order to span possible fault of both the actuators and the sensors, and with some machine learning technique try to see which is the let's say the envelope of the transient, if we are within some safety margin or not. But yes, and I think the main advantage is it's relatively fast running, which for some kind of reliability analysis it's very important, and can be parameterized, which is another, let's say, important feature for the reliability analysis. Yeah.
Thank you.
Great. Well, thank you very much to the three of you.